Hello, everybody, and welcome to your lecture on Earth structure. Do want to warn you that this is one of the most important lectures in the class, just because this is going to get you oriented to the very basic structure of Earth, which we are studying, right? So, anyway, do pay attention to this one. Take careful notes. You know, it's not a bad idea that besides your lecture assignment, you also take notes, maybe in the margin, things like that. So, this is very important. A lot of the questions that you encounter today on your lecture assignment will be on the test. So anyway, without further ado, we'll get started here, covering your lecture on Earth structure. So anyway, let's get a move on here. And first of all, we have to go over that very basic Earth structure. So the Earth has a layered structure. There's four layers, okay? That outermost layer that we live on, that you're used to, is called the crust, right? So there's the crust. Then beyond that, there's the mantle. The mantle is the very largest of those layers. It's actually the largest both in terms of volume and in terms of mass. So it's 2/3 of the mass of the Earth. So the majority of the Earth is the mantle. Now, the other 1/3 of the Earth's mass is here in the core, okay? So the core, we divide into the outer core. So I'll put OC for that, and the IC, the inner core, for this. And those are, well, we'll go through all these, right? So the crust is made of relatively light, stony material. So this is like low-density, stony material. The mantle is made out of relatively denser, stony material. So you might remember I showed you before some minerals of the mantle. I'll actually go and fetch some so I can show some more to you right now, because we actually do have samples of the mantle. So I'm going to cut a little bit and show you some samples of that. Hello, everybody. Just want to give you a little demo here of some of the rocks that we talk about in this lecture. So, we talk about ocean crust, and we talk about the continental crust. This rock here, this would be a basalt, right? So this is very typical of the ocean crust. Looks like this, just black and kind of boring, and no really like big visible crystals. These rocks here would be more typical of the continental crust. And you can see these are more like granites and diorites. But the thing I really wanted to show you here is the rock that's very typical of the mantle. So that rock is right here. So this is a mantle rock. And you might wonder, how do we get a rock from the mantle? Because we never actually drilled down that deep. You can see it's this beautiful green color, right? That's all from the olivine. That's olivine crystals that are in there. It's actually a gemstone called peridot. But anyway, how do we get this rock? It comes actually from the mantle from a volcanic event. So, volcanoes, a lot of the melts that form volcanoes, they start off in the mantle, and as they come up to the surface, they bring along hunks of the mantle. So you can actually see this black is the black basalt that surrounds it, and the green is actually a chunk of the mantle called a xenolith. So hope you like that. It's a pretty cool little chunk of the mantle, and we'll get back to the lecture now. Okay, so I hope you liked taking a look at those samples. Those are real samples of the mantle. So volcanoes, bring those up to the Earth. So that's what the mantle actually looks like. You get hold of a piece of the mantle in your hand. Beyond that, we have the core. Okay, like I said, the core now is different. This is going to be not stony, but it's going to be metal. So the Earth is actually rock and metal. The core is a metal iron nickel alloy. So that means it's a mix of iron and nickel mostly, but with other stuff in it as well. So it's probably like 90% iron, maybe 5% nickel, and about 5% other things in there as well, which is a topic of very hot debate in earth sciences and in geology in general. So anyway, going on with, then we have the inner core. Now, one thing you got to mention about the outer core, inner core is a liquid. The inner core is a solid. So inner core is literally the part of the core that has cooled down enough. Well, I shouldn't say cooled down. It's actually hotter. But it has crystallized in the center. And then the outer core is the liquid part, still a liquid. And slowly over geologic time, over Earth's history, that outer core has been solidifying. So it gets more and more. The outer core continues to grow larger and larger. The inner core continues to grow larger and larger. The solid crystalline part of it, and then the outer core continues to shrink. Okay. So anyway, that's that layered structure. You can see the crust. This is a cross-sectional view of the Earth. Like if you were going to go down from the crust, from the surface, right, and go all the way down to the center of the Earth, right? Now the center of the Earth is 6,400 kilometers deep. Okay. Now you can see that the crust is really just very, very, very thin, right? So there's the crust. And you can barely see it. It's just this kind of little purplish line that's up here at the very top. So it's really just, actually, it's sort of funny. It's really just kind of like the scum of the Earth that's risen to the top, and it's just this kind of thin layer of scum, or thin layer of foam almost. You can think of it sort of like that. It's not scum and foam, but it's the stuff from the Earth that's relatively lighter density, and it's risen to the top. So anyway, we'll get more into that as we proceed on through the class. But the mantle is underneath the crust, right? And then you have the core mantle boundary. I often call this a CMB. So sometimes in this class you might hear me refer to this as a CMB. CMB means core mantle boundary, right? Core mantle boundary, CMB. That is found about 3,000 kilometers down. More accurately, it's really 2,900 kilometers on average. Okay, so you also see a yellow line here. I want to point this out. You see this yellow line. It's called the geotherm. Geotherm. It's an important word. I don't ask about it in the lecture assignment, but it is an important word. Geotherm refers to the temperature gradient, or like the temperature profile through the Earth. So you can see up here at the crust, obviously the temperature is very low, right? It's very far to the right. Here's the temperature given to you on the horizontal axis scale. And you can see that it quickly rises until you get into the mantle, right? And then once you get into the mantle, the temperature gradient kind of decreases. But anyway, it gets down to the bottom of the mantle. Take a look. The bottom of the mantle is really here around, 3,000 to 4,000 Kelvin, maybe hotter, okay? Whereas here at the top of the mantle, if I draw a line down, it's really only maybe like 1,500 degrees Celsius, okay? So anyway, you can see there's a huge, this is important, folks, there's a huge temperature change here from the top to the bottom. So the top is relatively cool, right? There you go, it's cool. And down here at the bottom, it's hot, okay? So something to think about, right? Now, the Earth, just some basic facts about it. The Earth that's how many kilograms it is, 10 to the 24 kilograms. Now, that's equivalent to basically 1 trillion times 1 trillion. So the mass of the Earth is 1 trillion times 1 trillion kilograms. Okay, it's really, right, quite a lot of mass. The radius, like I said, is around 6,400, close to 6,400. And the density, you should know by now, is about 5.5 grams per cubic centimeter, okay? And actually, by the way, we are the densest planet in the solar system. We have the highest density. Now, very important, you see the first question you have is, what's the age of the Earth, right? So age of the Earth, obviously important question. It's going to be on all your tests, is 4.55 billion years, according to radiometric dating. That's the number that we've gotten from radiometrically dating the rocks, okay? And that is referring to when the Earth kind of accreted together, right? So obviously the Earth is, maybe you could say, a work in progress, right? So it grows over time, but it was mostly grown and put together and became a planet about at that age, about 4.5 billion years ago. Top 4 elements. So let's talk about the composition of the Earth, right? Remember, whenever I talk about composition, I'm talking about periodic table elements, okay? Elements of the periodic table. So we have 4 top elements. Those are iron, and that should make a lot of sense, right? Because you have core. The core is 1/3 of the Earth, and it's mostly iron. So iron's the number 1 element in the Earth. So Earth, big chunk of the Earth is just iron, okay? After that, you have oxygen, you have silicon, and you have magnesium, okay? So this is a pie chart kind of breaking down for you the composition of the Earth, and as I said, you can see more than a third of it is iron, and so a third of the core is approximately iron, and then there's also iron in the mantle. There's iron in the crust. You'll see that iron is one of the most common materials and the common elements in the crust. Very, very common element. And what's very, very surprising for a lot of students is that the second most common element is oxygen. So besides that iron, the number 2 is oxygen, and oxygen comprises about 1/3, close to 1/3 of the Earth. So wow, it's a vast majority of the Earth. Well, not a vast majority, but a majority of the Earth is iron and oxygen. Okay, you throw in silicon, then you're up to 15. That's 15%. So now you're up to like 70% of the Earth, right? Iron, oxygen, silicon. You throw in magnesium. Now you're at about 83% or over, right? So most of the Earth, the vast majority of the Earth, is composed of just these 4 elements: magnesium, silicon, oxygen, and iron. Okay. All the other things, like of course, there's some nickel. That's present mostly in the core. There's some nickel here at the surface and in the crust, but there's not very much, right? It's mostly in the core. Sulfur, we think there's quite a bit of sulfur in the core. Okay, so most of that sulfur is actually probably in the core, and that's really that's a little bit of a guess. We're not exactly sure if there is sulfur there, but we think that's one of our prime suspects for what we think is in the core. Calcium, you can see that number we are more sure about. Calcium is maybe about 1.1% of the Earth. Aluminum is maybe another 1%. And then what's amazing is that everything else, all the other 92 elements of the periodic table, are just less than 1% of the Earth, right? So they're very, very small abundances, very, very small concentrations, right? One thing that I find very fascinating is that the bulk Earth composition, so this pie chart that shows you the composition of the Earth, it is almost exactly the same as the composition of stony meteorites, the kind of meteorites that are called chondrites, okay? And it's a very amazing fact, right? So if you were to grind up the whole Earth into a powder, and you were to grind up the chondrites into a powder and test those powders at a chemist, you would find that they are almost identical. Okay, so why is that? It's because the Earth had come together over geologic time. It's come together from meteorite strikes over and over and over again, right? That's all that material is collected from the early solar nebula. Chondrites are just samples of the early solar nebula that provided the material that later became the Earth, right? Eventually became the Earth. So anyway, let's go on talking about the crust. So here's your beautiful crust, right? Place where you live. We kind of divide the crust up into the atmosphere. That's the gaseous part. The geosphere, that's the rocky part. The hydrosphere, that's the liquid water part. And of course the cryosphere, which is cryo, means ice. So that's the ice glacier part, right? Now the crust is only 0.6% of the Earth. So it's a very small part of the Earth. Very important part. Obviously, we live there. We care a lot about the crust. But it's funny because if we didn't live on the crust, if we were like mole people, we lived in the mantle or something, we probably wouldn't even pay any attention to it because it's such a small part of the Earth, right? It's less than 1% of the Earth. Okay, so it's a very small part. Over the continents, the average thickness of the crust is about 30 kilometers, but it can be up to 70 kilometers. Where do you think the crust gets the thickest? You have any ideas? If you're thinking it's over mountain belts, you'd be correct. So the crust gets the thickest over mountain belts like the Andes Mountains or the Himalayan Mountains, the Rocky Mountains, things like that. Okay. Now over the oceans, the thickness is different. So we're going to learn a little bit that there's actually 2 types of crust. It's extremely important that you all know this. I guarantee you this stuff is on your tests, and there are a lot of questions about it, and it really behooves students, really helps students. If nothing else, make sure you know like differences between continental and oceanic crust. So we're going to talk about that more. But over the continents, the crust is thicker. So you could see the diagram here. The crust is shown over the continents, pretty thick. It's about 30 kilometers, whereas over the oceans, it's a lot thinner. Okay, so maybe it's only like 5 kilometers, something like that, maybe up to 7 kilometers. All right, so the crust, what is it made of? So the crust is a little bit different than the whole bulk Earth, right? So you see this pie chart's different than the one I showed you before. Notice that the crust is mostly oxygen. So you see that iron is here, but it's gone from 35% in the bulk Earth, whole Earth, to only 4.7% in the crust. So you can see that the crust definitely has iron, has quite a bit of iron, but it's much less important than it is in the bulk Earth. And that's because when you look at the bulk Earth, you're looking at the core, which has, again, mostly iron. So the most important, and it's amazing really, the crust, the most important element is oxygen. So if you pick up a rock, what's amazing is that mostly what you're picking up is oxygen. The majority of it probably is oxygen. Any kind of rock you pick up. I can't think of, well, I could maybe think of a couple minerals that don't have oxygen, but a lot of rocks, vast majority of it has oxygen, and it's probably mostly oxygen. Silicon is up to 25% now, right? Followed by aluminum at 7.5%. So you look at the top four elements of the crust, you're up to oxygen, silicon, aluminum, and iron. That's probably going to comprise, again, about like 83% of the whole bulk Earth. So, the crust. So that's what's amazing, is that really you're talking about four elements in both the crust and the whole Earth that are really the vast majority of the Earth, right? So the Earth, you can see, is not a very chemically diverse place, or it's not a lot of chemical variation. It's just like four elements, and that's most of the Earth, okay? Now, in the crust, you throw in sodium and potassium also in greater abundances. You notice those weren't even included in the bulk Earth. There is some magnesium. There's some hydrogen from all that water, right? From all the H2O. And then everything else is in other. And that's something I find amazing, because does anybody notice something that's conspicuously missing here? Because I look at this and I'm like, where's the carbon, right? You're a carbon-based life form. The trees, the grass, everything, the wood, everything, that's all carbon. The plastic and petroleum and stuff, it's all made of carbon. Where's the carbon here? It's all in this other less than 1%. So 1.1%. So it's amazing. Carbon's so important for us and for our life, and obviously we're carbon-based. All life is carbon-based. All life is carbon-based. So, but yet very small abundance in the crust. Very, very small abundance in the whole Earth. Okay. So anyway, if you look at the periodic table, 90% of the crust is just these five elements you see right here: oxygen, silicon, aluminum, iron, calcium. 99% of the crust is, you just throw in another four: hydrogen, magnesium, sodium, potassium. Okay. One thing I want you all to be careful of, sodium, the elemental symbols, they make sense for a lot of the elements, right? But for sodium, potassium, obviously they don't. So K is potassium, right? That's actually potassium. And then this is sodium. Okay. But I think a lot of these make sense. Iron, obviously, is not. A lot of people, it's funny. A lot of people think this is iron. Let me see, iridium. They think iridium is iron right here. That's obviously not iron. That's iridium. This is indium over here, number 49. Iron is 26. So that Fe is from the Latin ferrum. So that's why you see Fe instead of IR or IN or I something. Okay. All right, so like I said, I promise you there's going to be two kinds of crust, and here it is. So you do have to know these two types of crust. I just highly recommend that you make sure you know this part, because like I said, it comes up a lot in the tests. And just knowing this, probably more than any other concept in the class, will get you a lot of points on the test. So just make sure you know this stuff. Continental crust versus oceanic crust. So the oceanic crust is mostly made of a rock called basalt. Okay, when we take a closer look at igneous rocks, we'll learn more about basalt. But for now, we'll just say it's kind of a black volcanic rock. It's not very interesting to look at. It's kind of plain looking, boring looking. And the thing about the ocean crust is that there's very little variation. We might call it homogeneous or homogeneous, right? It's almost all basalt, and that's it. there's not a lot of other stuff to write home about. Okay, it's just basalt. That's very different than the continents, because the continents have a lot of variation. There's limestone, there's sandstone, there's rhyolite, there's granite, there's everything there on the continental crust. But basalt, that's the ocean crust. Okay, ocean crust is really kind of boring. I feel sorry for geologists that have to study the ocean crust, because I think it's a really kind of a boring kind of rock. But anyway, the density of the ocean crust is about 3.3 grams per cubic centimeter. You notice that's a lot less than the bulk Earth. And it's also, I want you to keep this number in mind, 3.0 cubic centimeters. We're going to grams per cubic centimeters, because we are going to compare this to the continental crust in just a minute. Now, here's the continents. The continents are, if you were to kind of grind them all up and turn them into one whole homogeneous rock. Of course, it's not homogeneous. There's a lot of variation, like I said. That rock that you would get would be called diorite. So the average rock type is diorite. Again, it's hard because there's a lot of variation in the rocks of the continents, but the average is diorite. It's not granite. I know that your book says that it's granite. It says that the continents are made of granite. It's total BS. It's not granite. This is a myth that's been, I don't know, it's keeps going on in geology textbooks, like Geology 101 textbooks, but I can guarantee you it is not correct. It's diorite, which is different than granite. And we'll talk about the differences between granite and diorite and igneous rocks when we talk about igneous rocks. But anyway, there's a lot of variation in the rocks of continents. They have an average composition of diorite. We'll talk again more about what that means later in the class. So the average density of the continents is 2.7 grams per cubic centimeter. And you'll notice it's lower than the ocean crust. And a lot of you are like looking at this, you're probably like, okay, 2.7. That's basically 3. It's close to 3. What's the big deal there? It's amazing because it's actually a huge deal. It's a huge difference, and it's a very important difference. So if it wasn't for this, I could kind of say this, that the continents, if they weren't kind of buoyed up by its low density, basically the way you could think about this is the continents, if they were denser and if they were as dense as the ocean crust, they would sink more into the mantle, and the elevation of the land surface would be a lot lower. And in fact, I could say that probably only the mountaintops would be peeking out of the water. So it's actually amazingly important for your life and for my life that the density is 2.7. It's a little bit lower, and that helps us to have more continental crust to live on that's above sea level. Okay, so it's a big deal. Continental crusts have more silicon. Forget about aluminum. I'm sorry I put aluminum here. I have to eliminate that. But they have more silicon and oxygen. And they also have more sodium and potassium than oceanic rocks. So those are some specific chemical differences. Okay, we're going to see that ocean crust has more magnesium and iron. Continental crust has more potassium, sodium, and silicon. Okay, so here are the two types of crust, just compared and contrasted here. Continental crust is obviously thicker. Ocean crust is thinner, about 5 kilometers versus 30 kilometers. Continental crust is less dense, about 2.7 grams per cubic centimeter. Oceanic crust is more dense, and again, that's because it has more iron. Remember that it has a lot of that very dense element, iron. So this one has more oxygen. Continental crust has more oxygen, silicon, sodium, potassium, and I'm sorry again. Forget aluminum. It's really should put potassium there. Okay. All right. Another thing that I could point out, it's kind of obvious in a way, but obviously the continental crust has a higher elevation than the ocean crust, right? Ocean crust is on average 4 kilometers below sea level, 4,000 meters below sea level, whereas the continents are about 500 meters above sea level. Okay. So just keep that in mind. I do want you to just know that we're going to see this later as we talk about the mantle, but the mantle is really kind of a softie, And the continental crust and ocean crust can kind of, and does kind of, sink into the mantle. And you can almost imagine it like these blocks of wood that you see depicted in front of you. So that's a really important concept, because you shouldn't think of like, well, basically there's going to be this adjustment, right? If you could imagine, you can all imagine, like if I were to stack some ice on top of the crust right here, you know that this block of wood would sink deeper into the water, right? And the same thing happens with the crust. When you stack ice like a glacier on top of and this, you'll see this work out in this class a lot, okay, as we progress in the class. As you stack on more ice from glaciers, the crust, the ocean or the continental crust, will literally sink deeper into the mantle. And then if you relieve the pressure and you take that ice off, like if the temperatures warm up and the ice melts, that's going to pop up. Okay, the whole crust is going to pop up. So it's. I just want you to be aware. There's this like gravitational equilibrium. It's called an isostatic equilibrium. Okay, we call it isostasy. So anyway, just be aware of things like that. There's no questions like that in your lecture assignment or on the test, but it's just a concept you should kind of have some awareness of. All right, so moving along here, I want to talk about the mantle. Okay, mantle, like I said, that's the big boy of the Earth. That's 2/3. The majority of the Earth is mantle. Okay. The Earth is mostly mantle. I already showed you this beautiful sample of the mantle. Okay, so that green mineral that you see that's so abundant is olivine, right? So the mantle is the biggest part of the Earth, both in terms of mass and volume. The mantle is about 2/3 of Earth's total mass, and it's composed of stony material. It's denser than the crust. It goes all the way from about 100 kilometers, even more than that. I mean, the mantle really starts at, right? I mean, the mantle over the oceans, the mantle starts at 5 kilometers deep, right? There are actually some places on Earth where the mantle comes almost near the surface. So it goes in some cases pretty close to the surface, all the way down to 2,900 kilometers. Okay. So about half of Earth's radius is the mantle, half of Earth's radius is the core, basically. So the mantle extends down, like I said, 2,900 kilometers, and the temperature at that depth of that core mantle boundary, the CMB, is really about close to 4,000 degrees Celsius, probably. And it could be up to 5,000, for all we know. It's not super well bracketed, so we think it's somewhere in that range. So it's really fascinating, because if you think about this, you have a really, really hot core mantle boundary, and things are going to cool down as you move up here. So you can imagine there's going to be a tendency for hot material to want to rise, right, and rise towards the surface. And we do, in fact, see that happening, and I'll explain that in a bit. So the pressure also, I want you to think about pressure. As you move down through the Earth, obviously the pressure increases a lot. The pressure at the core mantle boundary is 134 gigapascals. That means 134 billion pascals. And you might be like, okay, that's nice. What the heck's a pascal? Well, a pascal it's a unit of measurement of pressure. Here at basically, normal standard air pressure that you're used to at the surface. Because, of course, remember, there's pressure here because you have the whole atmosphere sitting on top of you. And that atmosphere does exert a pressure on your body, on you. Okay? That exerts a pressure of about 100,000 pascals. So when you go down to the core mantle boundary, you're up at like 134 gigapascals, 134 billion pascals. So that's millions of times more pressure than what you're used to, right? So you have a significantly elevated pressure. Okay. I do want to talk about this thing. It's it's just a vocab word that you need to be familiar with. There's this thing called the Mohorovicic discontinuity. And everybody, though, just calls it the MOHO. Okay, MOHO is the word. you're going to encounter all the time. Okay, it's the moho. It's written there. So a lot of times if you're reading the textbook, you'll see it refer to the moho. Sometimes I refer to the moho or talking about the moho. So all it is just the boundary between the crust and the mantle. That's all it is. So the boundary that is between the crust and the mantle, simply just call that the moho. Okay, so that's all there is to it. We detect the presence of the moho by seismic reflections. So when there's an earthquake, seismic waves, of course, earthquakes generate seismic waves. Those seismic waves they bounce off of the mantle, the crust mantle boundary, that's the moho, and they reflect back up, and they can be detected by different seismometers. And from those travel times of the seismic waves, we can figure out how deep that is. So if you ever wanted to know, how do we know how deep the mantle is? How do we know how big the crust is? How do we know where the core mantle boundary is? How do we know what the core mantle boundary is made of? It actually all comes back to this process of earthquakes generating seismic waves, and then seismometers like seismographs and seismographic stations analyzing those seismic waves that come up from the earth. It works a lot, the same principle like an ultrasound, right? Ultrasounds work that way too. When they do an ultrasound, like on a pregnant lady's belly or something like that, to look at the baby, that's all working off the principle of acoustic mechanical waves. They're seismic. They're not seismic waves, but they're the same kind of wave as a seismic wave. Anyway, this is a really important fact. This slide, make sure you know this. This is very important for the whole class. It comes up again and again throughout this whole class. The mantle. So the mantle is, absolutely solid. Okay, it's totally a solid. There's nothing that is liquid about it. But it does, over geologic time, it does exhibit fluid-like behavior, which is shown in this little animation that you're seeing in front of you. So you can see that at the top of the surface of the Earth, you can see this blue material that's sinking down into the mantle. Okay, that's the ocean crust. And you can see that from the core mantle boundary, there's this red material that's relatively hot, and it's rising towards the surface. Okay, so that process is happening all the time in the mantle. There's convection. So the mantle, although it is a solid, it is convecting. So this is solid state convection that is constantly happening in the mantle. It's not a liquid, but because it is hot and under high pressure, it's able to kind of move and flow and exhibit fluid-like behavior. It's kind of a softie. The mantle's a softie. I almost compare it to I compare the mantle to kind of soft butter, something like that. Like soft butter is still a solid, but it keeps its shape, but it's soft and it's malleable. Okay, so it's a little bit like that. We do need to talk about this very important concept. This comes up a lot, again, in this class, is lithosphere and asthenosphere. So let me talk a bit about that. So the lithosphere, lithos in Greek means stone. And the sphere just means the shell, the part of, so it refers to the part of the earth that's stone-like, stony. Asthenosphere, again, is a Greek root. So sthenos means strength. Okay, and asthenos means no strength shell. Okay, sphere would be shell. So this is the no strength shell. What does that mean? So the asthenosphere, it's the part of the mantle in which there's convection. Okay, so once you get down to about, you can see that it varies, but once you get down to maybe 100 to 150 kilometers down, the mantle gets warm enough that it starts to convect, and there's convection. It's more malleable, and it's able to bend and fold and do all these things that the lithospheric mantle cannot. So above the asthenospheric mantle, there's the lithospheric mantle. That's the part of the mantle, and it's actually the upper crust and mantle. But that's the part of the earth that behaves like a typical stony sphere. Okay, it just behaves like stone. Like you hit it with a hammer, it cracks, it breaks, it fractures, it crumbles. It's like a cookie. Speaking of cookies, I think a really good way to understand this is that the lithospheric mantle, the lithosphere, is kind of like a cookie, like a baked cookie, and the asthenospheric mantle is kind of like cookie dough. Okay, so the cookie dough, you know, it's made of the same stuff as the cookie, right? That's the same composition. And that's true of the lithospheric mantle versus the asthenospheric mantle. They're made of the same composition. They're made of the same stuff, right? But the difference being that the cookie dough is kind of bendable, foldable. It can change its shape. It's still a solid, but you can fold it and change it and change its shape. Whereas the cookie, if you try to do that to the cookie, it'll just crack and crumble and fall apart, right? So that's kind of the difference between lithosphere and asthenosphere. It's a mechanical difference. It's a difference in the way that it deforms, basically. So lithosphere is the uppermost crust and mantle. It's mechanically strong and it's relatively cool. It's also mobile, so it'll move with the mantle convection. These are basically what the plate tectonic plates are made of. They're made of the lithosphere mantle plus crust, and they move with the convection of the mantle. And we'll talk about that when we talk about plate tectonics. The asthenosphere, on the other hand, the mantle, that's the part of the mantle below the lithosphere. It's mechanically weak. It's warm. It's not molten. It's not a liquid, but it's warm enough to be kind of ductile and deformable. Okay, so it's ductile and easily deformable, and it convects and it allows for the plate motions. Okay. So besides that, that's the mantle. The final part of the Earth we need to talk about is the core. Now, of course, we have an outer core that's liquid. We have an inner core that's solid. Okay. That core, inner core, outer core boundary is at about 5,000. So 5,000 kilometers. So you could see that the radius of the outer core goes from 5,000 kilometers to 3,000 kilometers. Okay, so if you're going down a trip through the Earth, there'd be about 2,000 kilometers of the 6,400 would be outer core. Temperatures in the outer core are about 4,000 kelvins, about 4,000 degrees Celsius. It's about 95% not iron, 5% nickel, probably 5% other stuff, and we don't really know what that other stuff is. Now, a really important part of the outer core, why it's very important, is that it generates our magnetic field. Okay, and just to kind of give you a quick demonstration about how that works, I want to kind of show you this experiment. Probably some of you have seen this before in grade school, but I do kind of want to show you this experiment, so I'll cut here to a quick demo. Okay, so I hope you enjoy that. Hello everybody, and welcome. This is a little demo I want to show you. It's maybe a demo that you might have seen in grade school or something like this, but basically the way it goes is this. I want to show you how circulating electrical currents can create or induce a magnetic field, and it's a very common demonstration. So what I have here is actually just an iron bar, iron just like what's in the core, right? What is circulating in the core. And you might see in the other screen down here we have some paper clips, and we have a little compass there. And of course you can see the compass is reacting to the iron bar, because of course there's a little magnet in the compass that is following the iron, right? So there's a little magnet in the white arrow that's following the iron, because the iron's magnetic. Okay. So anyway, what I'm going to do is I'm going to take a copper coil. This is just a little copper coil. Okay, you can see it there, and I'm going to slip it over this bar. Okay, so here we go. I'm going to put it over the bar, and there's going to be a coil of copper going around the bar. And what that does is when I put an electrical current through it, the electrical current's going to be circulating and spinning around, right? So it's kind of like a spinning current. And what that's going to do is induce a magnetic field, perpendicular, by the way, to the direction of the spiral. So I do have a little bit. You might wonder, how am I going to create an electrical current? I'm going to do that with this power supply. I got a DC regulated power supply right here, so it's a direct current. It's already on. You see I have it turned it on. And I'm going to take my alligator clips and I'm going to attach it to my coil and see what happens. So you can see, so actually what I can do right here is I'm going to position the iron bar like that, and I'm going to put on one of my alligator clips, and I'm going to put the other one right here, and you can see the sparking from the clips, right? So you can see that once I do that, you'll notice that now this compass is much more reactive. And you'll also notice that I can pick up, right, these paper clips pretty easily with the bar, and that's because it's been magnetized, right? So, and you'll also notice that if I switch the direction of the electrical charge, so I put the red where the black was and the black where the red was, you'll notice it'll switch the polarity. So now the red, see how the red arrow is following? The red arrow is following the iron bar, whereas before, when we did this, we had the white arrow following it. You might recall, see that? Okay. So now you see what I mean. So anyway, that's a little demonstration. Hope you enjoyed that, and go back to the lecture now. Okay, so I'm back. Hope you liked the little demonstration. So anyway, that's basically what the outer core does. It circulates. It is a ferromagnetic, material, so it's able to generate from its circulation a magnetic field, and that magnetic field is just really, really important for our life. It protects us basically from the solar winds of the sun, which are extremely hazardous to life. It protects us from kind of the really nasty ionizing radiation that is generated by the sun. So again, life on Earth probably we wouldn't have had the same kind of development of life on Earth if it wasn't for our liquid outer core and its generation of the magnetic field. Okay, so it's an extremely important part of Earth, and probably you've never even thought of it before. One thing that's really cool about, you might ask, like, how do we even know that the outer core is solid or liquid? And the reason is we don't have a sample of it. We've never gotten a sample of our core. What's kind of fascinating is we actually have samples of other planets' cores, but we don't have a sample of our own core. So the reason is that there are some planets that used to exist in our solar system that they exploded, they collided and exploded, and we actually do have samples of their cores. Those are the famous iron meteorites. Okay. However, we do not have a sample of our own core because we haven't exploded. So, and luckily for that, right? So we don't have a sample of our own core, but we do know that it is a liquid and not a solid, and that's because certain seismic waves from earthquakes cannot penetrate liquids. And so we can see that those kinds of seismic waves, what are called S waves, do not penetrate through the outer core. So that way we know it is definitely a liquid. All right, going on to the inner core. The inner core is solid. The iron-nickel alloy probably has some other lighter elements, and extends from the base of the outer core 5,000 kilometers to 6,400 kilometers deep to the center of the Earth. So that's the outer core, the inner core. There's not very much to say about it. It doesn't come up very much in this class at all, but the outer core does. So make sure you know the outer core. So that's all there really is to it. I will stop here, but hope you enjoyed the lecture. Do hope you have a good week, and I will talk to you very soon next time. Thank you for listening.